Hello, good afternoon. I'm Dave. I'm in from Carmel, Indiana, back in the United States. I've been working with F# for a number of years now, although I have to confess that the past few years since writing the book of F#, my career has not necessarily allowed me to write F# as much as I would like. As many of you can imagine, I'm sure, you end up in shops or working for a company that says, we're a C# shop. And they frown upon trying new things. So that's been kind of my life since I wrote the book, but that doesn't mean that my enjoyment of the F# language has diminished. And in fact, every time I work in C#, there are plenty of things that I miss daily. There are a number of things I found workarounds for. There's a number of things that the C# language team is working on finding workarounds for, but they're usually not anywhere near as close to what the F# implementation is. So I do miss working in F# daily, and I hope to make that, be able to remedy that in the next few weeks here with an upcoming project. But before we get started here, my publisher was kind enough to give me a few copies of the book to hand out here at NDC London. They're up on the front table, and they also sent enough stickers for, I think, the entire conference. I don't want to take these books back with me because they end up on my backpack and there's a long time in the plane. And even with those tossed up, I've got to run across the airport. So my friend Brian is going to be monitoring tweets, and he will be in charge of distributing those books. So if you already have a copy, please leave it for somebody who does not have one. But otherwise, those will be handed out at the end of the session. Aside from that, again, I'm Dave, consultant back from Indiana, and this is the Book of F# 60-minute Human Edition. So I think, for me, my story seems to be pretty typical from the people I've talked to, of people coming into F#. Why F#? I was a C# guy basically my entire career coming into this, and I didn't really set out to learn a functional language. I just kind of stumbled upon it by accident. And for me, the gateway was a little technology called LINQ. I'm sure that sounds pretty familiar. But what I found over time is I really liked the patterns that were evolving out of LINQ. And I looked at the query syntax initially, and then I started looking at the method syntax, and I'm like, wow, why do we even have this query syntax? Like, this isn't SQL. And that whole method chaining and delegation approach just really resonated with me. It made so much sense, and soon my code started looking like LINQ. Like, I was writing functional code at the time. I just didn't know it back then. But as I learned about functional programming, and as I learned about the advantages that it has over more traditional methodologies, I started learning the terminology and giving names to what I was doing, things like first-class functions, and realizing the advantages like the default immutability and the improved predictability of the software. I really fell in love with the functional paradigm, and from that I learned about F#. So F#, strongly typed functional first programming language for writing simple code to solve complex problems. Great blurb of marketing speak. Oops. Yeah. But it doesn't really give the whole picture, because F#, yeah, it's a functional language, and that's just for the academics and the financial companies, right? No. It's a general purpose language. So we can write whatever type of software we want. But it's also a hybrid language. It's a multi-paradigm language. It just happens to be a functional first language. What that means is that it's actively trying to guide us into writing code in a functional paradigm. And then when we need to, like when we're using a library that's object-oriented, we can revert back to that. And we can fall back onto those different paradigms as needed. But overall, it's going to really try to guide us toward writing in that functional style. So there really isn't a formal definition of functional programming. You talk to 10 programmers, you get 10 different answers. This was kind of an aggregate definition I came up with at one point, that functional programming is a paradigm which concentrates on computing results rather than performing actions. So we're not going to worry about managing state, we're just going to worry about inputs and outputs. And to me, functional programming is really built on 3 pillars. First is taming side effects. You'll hear about things like, well, you can't have immutability, you can't have side effects. And that's the wrong mentality to me, because the ultimate goal of software is to have some effect on the world, right? Whether you're writing to a database or calling some service, you're changing the environment around you somehow. It's not about eliminating them, it's about taming them, getting rid of global scope, that type of thing. You get rid of that, you can control if you have to have some type of mutability, whether you're changing the contents of an array, limit it to a function. Don't get rid of it altogether. The second pillar is about emphasizing expressions. So C# is a statement-based language, right? F# is expression-based. And that offers a number of advantages in itself. One, everything has an input and everything has an output. Well, if everything has an output, that makes it much easier to understand what's going on inside of some piece of code. So if there's an output, you can also check what that output is, right? That means it's easier to test, and it's easier to predict what's going on. And the third pillar is functions as data. So we have our ints, we have our strings, we have our custom objects. Well, functions should be treated no different in the language. We're not going to really emphasize functions as data so much in the overall content of this talk, but we'll see it repeated throughout. We've talked a little bit about these advantages, and I know this has been a heated topic as the past week or so has gone on about whether we should be relying on the type system or whether we should be relying on our unit tests and our integration tests. Well, first off, I don't think there's an either or. I think it's a both. But I've always been of the mindset that if the computer can do something for me, why wouldn't I let it? Let the type system do its job. Let the type system stop me from making stupid mistakes that we all make from time to time, right? You know, I liken it to a saw. My dad was a big woodworker, and he had his table saws, and I'd see these saws in the garage, and they'd have an exposed blade. You know, how many times do you hear about somebody in a wood shop that's got this table saw sitting out there and they run their finger through it? Well, there are things you can put on top of that saw to stop you from running your finger through it. There's also things that you can take off of the saw that will allow you, but do you want to rely entirely on making sure that you're paying attention 100% of the time? Or do you want to have the language and the compiler stop you from doing those types of mistakes to begin with, and then give you the flexibility that when you say, yes, I know what I'm ready to do, I can take off that safety? I tend to go for the form, for leaving the safety on. So this is the first example in the book. I opted in the book to not go with a hello world example because everybody does hello world, and when a language like F#, it's one line of code. And one line of code doesn't really tell you anything. But this example, it's just a reverse Polish notation calculator. And it doesn't include every aspect of F#, but it involves numerous aspects. And I think, just based on its conciseness, even those of you who have not used F# or looked at F# can probably discern some idea of what's going on in here, right? We have a thing. Oh, it looks like it takes a string, and okay, there's this other thing. Let solve items in current. Oh, okay, that means is that a function? It kind of looks like it's doing something. Match current and items. Okay, I'm doing something with those that current value and that whatever is in items. Items must be some type of collection. It's plural, right? And then we can see, plus, minus. Those look awful familiar. I'm pretty used to those as my mathematical symbols. And then we can see, s.split. Well, s is coming in from somewhere, but split, I know split. That's a method off of the string, so I must be taking a string and breaking it apart on the spaces, and then I'm executing some method to solve this for every variable. So if you know that reverse Polish notation is taking a string of expression or string of numbers and operations, you can have a pretty good idea that maybe it looked like something like this. The input, 2, 3, plus. So it's going to push 2 and 3 onto a stack, and then plus is going to evaluate. Oh, well, that's right here. Plus, we're going to pop the y value because that's the one that was put on last. We're going to pop the x off because that was the one that was put on before. And then we're going to do some operation. Well, what's t? T is the rest of the items in that array that came out of split. Similarly, we have 5, 4, 6 plus divide. So all of these things you can discern very quickly, mapping back mentally from the input of the string back to what the calculator is doing. So the magic behind F-sharp, now, and this is the thing that I think is probably the most important of all of the things in the F-sharp language. How many people have heard of curried functions? Okay. So to me, this is really, as I mentioned, the most important thing in the way that F-sharp behaves because it opens up all of the rest of the expressiveness of the language. So you think about a C-sharp application. You call a function. You have to give it the arguments, right? You have to say it's an add function like this. You give it A and B. Those arguments are applied at the same time. They always have to be supplied together. In this case, we see let add A and B gets A plus B. And our sum, exactly what we would expect. But notice in F-sharp, we don't have parentheses around our arguments. We're not grouping them. We're not comma delimiting them here. We're just passing them along. We know that from our math classes and years of experience that adding 10 and 5 should give us 15, and it does. But the signature of that function is int goes to int goes to int. We can even see that if we hover over this back in the code sample. Val add a of int goes to b of int goes to int. So I'm taking two integer values and getting an integer value back. But I'm not doing it the way that C# does it, because the F# compiler gives us curried functions. What that means is that it's really giving us a function that returns another function. And in F#, every function must have exactly one input and exactly one output. You don't have things giving you multiple return values, and you don't have things accepting multiple inputs. If you think about working in C#, if you're trying to work with your delegate types, which is essentially what's going on here. There's a separate class of delegates, the family of F# func versus func and action and predicate. You think about the complexity. You look at your link signatures. I think there are 9 generic overloads of func. I think there's 9 or 10 generic overloads of action. Well, if you've written your language in such a way that every function has just one input and just one output, that eliminates tons of complexity right there. And it also means that the compiler can make more decisions about how your code should behave and what it should do. So our add function that we saw back here, let add a, b, gets a plus b, is really saying let add a get a function that accepts b and returns a plus b. So that seems like, okay, whatever, that's odd. That's a little different way of thinking about this. What does that really matter? Why is this such a big deal? As I mentioned, currying is the key to unlocking the expressiveness of the language. The first point that this brings us to is what we call partial function application. This is where we apply just the first n parameters, n arguments, to a function to give ourselves a new function. So in this case, I've taken that same add function, and I've defined a new function called add 10. And notice all it's doing is saying add 10. I don't have any lambda expressions here. I don't even have to tell it a separate parameter, because the F# compiler is smart enough to know what the signature of add is. It knows it takes an int and gives us a function that takes another int that returns an int. Well, there's an implicit parameter on add 10, and we can see that the signature of add, remember int to int to int, has now become int to int on add 10. So every time we want to call add 10, we're just going to basically be supplying the b parameter to add. Remember, everything's an expression. And even in the C# world, our custom operators are functions, but we can't treat them as such. In F#, we can treat all of our operators as functions. So we change them from being infix to being prefix here. So if I want to create a convenience function for doubling values, double. I wrap the operator in parens, give it 2 as its first argument. Just like with add, we only supply the first argument for add 10. Now we're just supplying the first argument for our operator. And so we can do 12 is the result of doubling 6, and 30 is the result of tripling 10. But a little bit more practical is when we get into pipelining. So while partial application allows us to just specify a certain number of the parameters up front without specifying the rest, pipelining lets us chain our functions together in a very logical, consumable, and composable way. And I say here, data seamlessly flows from one function to the next. So when you think of when you're looking at pipelining, just think of it. You have this piece of data that's going to flow through the pipes and go through some series of operations and come out the other end. Oops. Taking this simple example, take our add function. Sometimes we just want to do it and throw away the result. So I threw in the ignore function. I don't care what it's doing. I'm just going to throw it away. Ignore is built into the language because F# requires that everything returns a value. And so if you want to explicitly not do anything, say you've made a function that updates the database and it returns the number of rows affected. You may want to check that. You may not want to check it. If you don't want to check it, you can ignore it. But because of the nature of the language, if you don't put the ignore there, then the compiler says, hey, you're not using this value. I'm not going to just throw it away unless you tell me to. So it's a compiler warning that you haven't used some return that may actually be important to your code. How about this? I come from the United States. We have a different temperature system. So this has been useful for me this week. Look at my watch. I see, luckily my watch does this for me, but I turn on the TV and it's telling me it's like 0 degrees. I'm like, wow, that's really cold. And it is cold, but how about a little conversion function? I'm going to take the degrees Fahrenheit and I'm going to convert it to Celsius. What I've got here, though, average temperature. So I just threw in a couple of random. We had a little bit of a hot spurt at the end of the week a couple of weeks ago back home. And we have 30, 32.8, so a good range, right around freezing with a warm spot at the end. I want to take those values. I want to average them. F# has a module built in for giving us an average. But notice I've turned it around. I've changed the semantics of the code here. I don't care right away about the average. Yes, I care about it. It's still important. But I don't care about it first. What I care about first is the data that I'm working with. So I have my array of these 5 or 6 temperatures, and I use that pipe forward operator to send that array into the average function. That's going to average those numbers together and give me the result. I don't need an intermediate variable to store that result. I don't care about the result outside of the scope of this pipeline. The only thing I care about here is what the average temperature in Celsius was. So let average temp get array, pipe to array average, pipe to Fahrenheit to Celsius. So this is how you can write much more concise, composable code, emphasizing the pieces that are important to your software. It gets out of the way. You write this, you care about, in this case, again, we care about the temperature, we know the series of operations in a very linear process, and we don't have any extra code noise to distract us from the problem that we're actually trying to solve in this block of code. And this is very idiomatic F#. So you'll see this all over the place. The fact that it allows us to emphasize those important pieces keeps us focused on the problems we're actually trying to solve instead of making the compiler, instead of doing things to make the compiler happy. I gotta fix my presentation here. So let's talk about some of the types that are built in to F# a little bit here. So first, we have the tuple type. How many people have used tuples in C#? How much did you enjoy that experience? Right, exactly. What the hell does item 1 mean? Right? You have no idea what any of these things mean. And it's so cumbersome to work with. Okay, yes, let me litter my code with tuple.create. That sounds like a good time. Now, that's going to really add value to my business partners, right? No, I want to write that. And I know it's coming in C#7, but it's not as good as this because the type inference is so much better here. I've got let point get 10, 12. The compiler knows, because of the comma, if you see a comma in F#, it's a tuple, with one exception. And it knows point is float times float. And that asterisk, because this falls into a category of data types called algebraic data types, that is really the sum of, it's really the product of the universe of floats and the product of the universe of floats. So every possible float value and every possible float value is a valid pair, in this case, a tuple. And we can pull data out of this. So even though we're just passing it around as one value, we have point. We can reference point anywhere we want within the scope of this. We can pass it into another function that accepts a pair. We can return a pair because it's one data type, right? It's containing those two values, but it's still just one data type. It satisfies that exactly one input, exactly one output. But we can pull data out. The first thing we can look at is just some simple, easy convenience functions. First and second, pretty easy. FST, SND. I think it's pretty implicit what they do. It gets you the first item and it gets you the second item. You've got to be a little careful with these, though, because if you try to use them on a tuple that has more than 2 items, it's not going to work because these are constrained based on the type system to a 2-member tuple. But we can also do, and this is our second glance at what we call pattern matching. We have a let now. Let x2, y2 get point. The compiler knows that point is a tuple of floats and knows how many items are in there, so it can drop those into the appropriate names. We have x2, y2. Records are conceptually similar, but the compiler has to create a type to hold them for us. Oops. Yeah, there we go. Simple example. We're really just trying to group 3 pieces of related data here. Red, green, and blue values. Pretty standard. Think about how much code you'd have to write to do that in C#. Even taking advantage of things like auto-implemented properties, keeping in mind that these are also immutable by default. So By default, you can't change the contents. You can do what we see on line 4, which is a copy and update, which gives you a copy of, in this case, red, and changes the G value to 255. Notice the suffixes. It's going to enforce the data type, so it's not going to do an implicit conversion. There are no implicit conversions in F# because that's a side effect. You're changing what you think about the environment. But if you think about what you'd have to do to implement this, how many data transfer objects do you write that are basically just a series of properties? This is that plus a whole lot more, because this is going to give us structural equality instead, in addition to just having a series of properties. So you can take any two arbitrary RGB colors, and it'll generate the code behind the scenes to override get hash code and equals. You don't have to do that, and you can take any two arbitrary values and do equality comparisons, and it'll look at those values, and it'll understand whether they are representing the same data. Not the same object in memory, not the same object reference, the same data. But if you want to use these as a DTO, there's one little trick you need to do. We have an attribute called CLI mutable. What that does is it instructs the F# compiler to generate the appropriate code for working with serialization so that it can actually create one of these through the default constructor and then set the values and whatever it needs to. So this does not change inside of our code whether or not the F# sandbox is going to treat this as mutable. It's still going to be immutable in our code. So we still, even though we can serialize it back and forth across the wire, we still have the benefits of immutability within our sandbox. And if you want to see something a little bit more involved, pattern matching against records. A function, getColorName, we're passing in the color. We're going to match color with 4 possible patterns. The first one is just looking for reds. Second is looking for green, and the third is looking for blue. And the fourth is just give us the hex value of whatever else comes in. One of the things that the F# compiler really forces us into, though, is because it knows all of these things about the underlying types, because it knows that an RGB color has just these 3 properties, and they are all bytes, it knows whether or not you've actually handled all of the possible cases that could come into here. So we have 3 record patterns to identify the 3 named colors, and we have 1 general variable pattern that's going to catch everything. We just called it C, and we use the string formatter to generate that hexadecimal value from that RGB color. And notice we just access the values, the individual values, exactly as we would if this was any other object that we were working with. Color.R, color.G, and color.B. So we still have all of that benefit. We don't have to change our mindset on how we need to work with this. I've got a color, I know what I need to get out of there, and I can just access it by property like I would on anything else. And then we can see some piping, taking red, pipe to getColorName, and then we do a copy and update, red with G equal to 100, pass that into getColor. And I'm emphasizing I care about the color. I don't care about the operation until after the color. Now the cool one, really cool one. Discriminated unions are one of the things I miss the most when I'm working in C#. I think that's, from the people I talk to, this is pretty universal opinion. Discriminated unions restrict the values to a known set of named cases. So how many times are you working on something, you know there's only ever going to be 3 different possible implementations of some base class. But somebody else could come in and extend it, right? Maybe somebody else say, hey, I need this custom writer. I don't need this the writer that we provided out of the box. Discriminated unions can provide us with additional safety to make sure that we're always working within the known set. So here's one possible use for discriminated unions. We can treat them as simple object hierarchies. So I'm working on a drawing program, and I'm going to say I'm only going to support in my minimum viable product release circle, rectangle, and triangle. I haven't implemented anything else outside of there. I just want to handle those three tools right now. Well, now when I write code, I don't need to worry about somebody else coming in and saying, well, I'm just going to throw in an oval because I think I can. No, the code that's working on handling that rendering doesn't understand how to work with ovals yet. So we can enforce that and make sure that everything is added in the right place as we expand, and make sure that the compiler can check it when we try to do something that's not supported. Now, just like with records, we also get some structural equality comparisons off of this as well. So we can say all of these circle, rectangle, and triangle, they are all shapes. You can think of, in this case, to help, think of shape as an interface or something, or a base class. And then circle is the implementation. Rectangle is an implementation, and triangle is an implementation. And they all have their own associated set of properties. Radius doesn't make sense for a rectangle, but it does for a circle. And notice that we can name them. And they look a lot like how we had named things in the record. It's very nice, simple, consistent syntax. But we're bringing multiple pieces of data in for some of these. So like the rectangle and the triangle have additional dimensions that they need to worry about. So we use the asterisk. Remember what asterisk meant? It's tuple. This is what we call a syntactic tuple, though, because it's not really a tuple behind the scenes, but it's the way that the compiler uses the tuple syntax to represent multiple values being associated to a particular union case. And then we just create those like we were creating an object. If we were in C#, we would have to have new here, but we're not there. The only time we use new in F# is when we are working with idisposable implementations. But we say circle, we give it 3. For the radius, we give rectangle 10 and 12, and so on. But notice this bottom option, that square, is not highlighted by the syntax highlighter here. Because square is not defined on that union. And so if we were to compile this code, the compiler would catch that and say, you've tried to do something with a union case that's not defined. So we either need to go and remove that code or implement square. This is a little bit more involved example. So we can also use discriminated unions as trees. This is really, really convenient for abstract syntax trees and stuff. It would have been really cool if Microsoft would have used this for Roslyn, but they didn't, because it's so perfectly suited for it. So this is very, very rudimentary here. But I've got a markup type just really intended to represent either some HTML or some XML. In this case, I went with HTML. And we say we're going to have content elements, we're going to have empty elements, and we're going to have just content. Our content element is going to have a tag name, and it's going to have a list of children, which will be additional markups. So we can have these giant trees, if we want, consisting of content elements, empty elements, and content. Empty element just takes a string. That's going to be the tag name. It's going to be like your line breaks. And then content is just going to be some basic text. You can see how we can build this up in a very composable way. Content element of HTML, content element of head, and we can see the nested lists there. If we want to work with that, we can use pattern matching. I want to convert that HTML structure, that markup structure, to a string. This is all the code I need. Yes, it's rudimentary. Yes, I haven't implemented attributes or anything like that. It wouldn't be hard to extend to do that. But we have to HTML string. That rec keyword, what is that for? Any ideas? Let rec to HTML string. That's to notify the F# compiler that this is a recursive function. So recursion plays a major role in functional programming. We tend to favor recursion over iteration, and the F# compiler is smart enough to do tail call recursion to do optimization so we don't blow our call stack, and it makes things a lot easier when you start writing things, when you're working in a functional language and start thinking more in terms of recursion and just calling functions over and over rather than thinking through iterations. But here, what we're going to do, match markup with. Is our markup a content element? If it is, let's pull out the tag in the children. Use. We're going to use this class, the string writer, to build up some string. What's really cool, this is the equivalent of the using statement in C#. It's going to go out of scope and dispose at the end of that 3-line block. So it's constrained right there. The F# compiler will automatically clean up after that disposable when it's done within that block. We're just going to take the children, and we're going to pipe it. Remember that piping is so important in F#. We're going to pipe it to a map function. So this is going to do some transformation against every element within that list. Well, what's it going to do? Oh, it's going to recursively call to HTML string. So if we have that, if we look back at our previous slide, content element HTML. Okay, now let's look at all of the children in that array. So the content element head. So it's going to start recursing through that entire structure, looking for whether each element in that array is a content element, an empty element, or just straight up content. And ultimately, we'll end up with some HTML if we do some HTML to HTML string. But that's all the code. So you think about that in terms of like abstract syntax trees. You want to handle various operations. You can define a discriminated union that will allow you to represent those pieces of your syntax tree and very easily write a pattern match expression to handle converting that into the form you need. Whether it's something like expression trees in like Entity Framework or something like that. These things, they're so much more concise and allow a lot more expressiveness in the way you write your code. And in fact, there's a piece we're not going to talk about in F# more than just this passing mention, but we have a technology in F# called quotation expressions, which rely heavily on these discriminated unions. And it's exactly that. It's an abstract syntax tree, and it allows you to inspect the structure of your code and transform it into some other structure, just like what we've just seen. All right. Now, the answer is on the screen, but anybody know what that is? That's the thing that exploded or something. Yes. So this is depending on which source you read, the Mars Climate Orbiter. And it was a very expensive piece of equipment that got blasted off into space, and everybody crossed their fingers and said, hey, go get us some data about Mars. Well, as it came up close to Mars, the trajectory calculation was off, and it hit the atmosphere and promptly burned up and got no data. The trajectory calculation was off because one team used one unit of measure and another team used another unit of measure. So going back to the discussion about should we rely on unit tests or should we rely on the compiler, this is one of the things that really sold me on F#. Because when I was learning F#, I was working on a project where the project was an optical character recognition, and we had to run these documents through a scanner, and we had all of these different templates to figure out where pieces of data were on that. And we had to convert that from the physical world to the digital world, and so we were dealing with DPI and inches and trying to manage where those little rectangular areas were. And I couldn't count the number of times that I forgot which function I was working with, whether I needed the DPI or whether I needed the inches. So, yeah, we can have a team coding standard that says, okay, well, let's just make sure that all of the parameters identify what the unit is. Let's make sure we've got unit tests behind this. But F# gives us built-in units of measure. We can annotate our data. We can annotate. Typically, we'll use it on floats. Our values with these units of measure, and the compiler will say, "You didn't give me the right type." Now, you can't see it here. We'll actually jump over to the editor and see how the compiler flags these in a minute. But to define units of measure, and these are much more involved in this in the long run. You can do all sorts of comparative equations and do conversions between the different types. They're really powerful. One thing to be aware of if you do use these, though, they are erased. So the compiler is fully aware of them, but they are an F# only thing. If you look at the compiled assembly, these will not be there. There will be no signs. It's kind of like working in TypeScript with interfaces. JavaScript doesn't have the notion of an interface, so it just goes away. But the TypeScript compiler handles it. It's the same thing here. The annotations just go away. And one of the reasons I like this, though, is notice we define the measure types. So we've got type F and C for our Fahrenheit to Celsius conversions. But notice how it looks like a generic, a type parameter on the values. I like that. It's a consistent way. I just know, oh yeah, I'm going to modify this value somehow. But now, my Fahrenheit to Celsius, that's the same function as before, except now I'm accepting a float of F. And on the Celsius to Fahrenheit, a float of C. So when I'm calling these functions down below, I have to give it the appropriate unit of measure. So only the first line of these 2 3-line sets actually work. And I'll jump over to the editor in just a moment, but you'll see. So for Fahrenheit to Celsius, I'm starting off with 212 degrees Fahrenheit, boiling, right? If I try to pass in 212 degrees Celsius, which is a very different temperature, the compiler won't let me. And if I try to pass over a value that doesn't have a unit of measure, the compiler won't let me do that either. But what else is interesting here is, anybody notice as we've looked at these functions that there haven't been return types identified in most places? I've annotated most of the places where I've had parameters coming in, but I haven't annotated what is coming out. Because the F# compiler infers what the output type is. It also has an implicit return because everything, one input, one output, it's evaluated top-down. The last thing it's evaluated must be the return. So we don't even have to tell it the return in most cases. So what I'm getting out of here, though, if I look at Fahrenheit to Celsius, I'm accepting a float of Fahrenheit, but the result of that is a float in Celsius, and we can even see the conversion happen there. So then, if I've got this in a pipeline that I'm working with Fahrenheit, and now I need to start working in Celsius, the compiler will enforce that everything from that point on is Celsius. So I can't just pass the Fahrenheit values into those Celsius methods. So let me jump over to Visual Studio Code. Also wanted to kind of point out that I'm running this all on a Mac. One of the big things that people say is, well, it's so tied to Visual Studio, and I've got to be on Windows. Well, I'm running this in VS Code on my Mac. My virtual machine is not running. So let's go find that first block. There we go. Got a couple other things here. There we go. Let's trash that. So here's that same code. And notice when I'm trying to pass the Celsius or the unannotated version, the compiler is stopping me. That beats a unit test every time in my book. Because now I don't have to maintain that, and I know that the code, the data that I'm passing into that function everywhere. I don't have to write multiple tests across the application for every place this is called. I just have to write the right annotation, make sure I'm getting the appropriate value. I think that's a really cool feature. That's one of my favorites. The error message is actually type mismatch. So expecting a float of C goes to object, but given a float of F goes to float of C. So it's confused on what unit of measure that it should be using. Yeah, one thing that is kind of, before we move on, when you're using units of measure, so we're doing this conversion. When you're working with these, you're going to have your signature says, okay, I'm getting this, I'll stick with Fahrenheit to Celsius. Our signature says, we are going to accept a float of Fahrenheit, and we're going to be returning a float of Celsius. But because those are not compatible, there are no direct conversions between those, and remember that F# doesn't do implicit conversions, we need to strip those units off, and then when we're done, we need to pop those units back on. So the first bit, line 328, float of T, that's F# version of a cast. So this is how we strip the units off. So T that came in, our temperature, was annotated as Fahrenheit. We want to pull that value off to treat it as a regular float. And then when we're done doing our calculations, we multiply it by 1.0 C, and that's going to do our conversion back to centigrade, because we can do the conversion, we can do the multiplication against the float and have and tack on the unit of measure. All right. All right, how are we doing on time here? Just about. Okay, cool, right on time. We've looked at pattern matching quite a bit, and this is one of those things, I know that the pattern matching is coming in C#7. No, it's not. When you've worked with this, no, it's not. It really isn't. And then every time you get excited, like, oh, they're bringing in pattern matching, and you see the list of things that they're going to support, and then they cut 90% of them. You're like, no, they're not. This is one of the things that will probably, I will be amazed if we ever see it in C#. So this is active patterns. And we can do pattern matching against variables, we can do it against constants, we can do it against records, we can do it against discriminated unions, we can do it against arrays and sequences, and so on and so forth. Those are all the built-in patterns. But what if none of those really match what we want? What if we want custom logic around how we match data? Active patterns are the answer to that. So everybody knows FizzBuzz, I'm sure. Well, this is probably a completely overkill solution for FizzBuzz. But look, I've constrained myself into the 4 values that the FizzBuzz requirements are supposed to allow. It is very explicit what my values are supposed to be. Fizz, buzz, and in this case, other, because what are the requirements? Fizz, buzz for multiples of 3 and 5, fizz for multiples of 3, buzz for multiples of 5, and the number for everything else, right? Well, how's that? Like fizz, buzz, other. Match, we're going to build a tuple right in our match expression. We're going to match n modulo 3 and n modulo 5, and we're going to do a little bit of tuple matching. If both are 0, both are evenly divisible, well, then it's FizzBuzz. If it's only divisible by 3, and we don't care what the result, that's what the underscore is, that's our wildcard pattern. We don't care what that is. We're not using it for anything. It's got to be buzz. The reciprocal for buzz, and then for everything else, we don't even care whether it's a tuple. Now, the compiler will enforce that it's a tuple, but we don't even care that it's a tuple on the last one, so we just use the wildcard against everything and return other and attach that value. Then our FizzBuzz, we have our shorthand for pattern matching, so there's actually an implicit argument here. You can see in the IntelliSense val fizzbuzz arg1. So the compiler has given us a parameter. We don't even have to do that with this to tell it explicitly in the syntax. Some people like this way, some people don't. I tend to go this way when I'm writing this. I know a lot of people do like to be explicit, but I know what function does. So now all of these union cases, what looks like union cases, are our active patterns. They all correspond back up: fizz, buzz, fizzbuzz, and other. These are awesome. I love these. But for reasons unknown to me, and maybe somebody in the room knows, I've never been able to find an answer. They're constrained to 7 cases. I don't know why. Do you know, Brian? Yeah, I've never been able to find an answer to this. But there's, for some arbitrary reason, and Don probably had a very good reason when he designed the language, they're constrained to 7. So if you have more cases than that, you need to rely on what we call partial active patterns. And these are basically the same thing, except we have a special type of function now called a, crap, I can't remember, I just drew a blank on it, I'm sorry. But these are new functions defined. And the syntax on them is a little unusual. We're going to say match this pattern. That's a pattern right there. Fizz or anything else. What this is converting to is we see some fizz, else none. F# has a built-in discriminated union called option. This is our way around null. There was a tweet a number of years ago, basically when I was writing the book. One of the people very prominent in the community responded to a tweet about what can C# do that F# can't, and the answer was null reference exception. I still love that. I actually have the image saved somewhere. It's pretty funny. So the way we get around nulls is it's an opt-in mentality. We have either some value or none. And none you can think of kind of like null, but it's much safer. And here, if n is divisible by 3, we're going to return fizz. Otherwise, we're going to return buzz. So we don't need a third case for fizzbuzz because it's going to be covered by default, just by virtue of having those two already. When we get into our pattern match down line 5 through 9, if fizz and buzz, return fizzbuzz. If just fizz, return fizz. So then we're even more explicit. When we compare that back to here, we were returning those values as part of that full active pattern, but now we're being a little bit more picky because we're just saying now we're going to look at fizz and buzz. And this allows us to get past that 7-case limit. All right. Yeah, I got time. Okay, awesome. How many people have heard of type providers on F#? Okay. Aside from currying, this is probably the other biggest thing that really sets F# apart from other languages. So, got a fairly basic description here, but type providers are components that provide types and functionality based on some typically external source. Things like databases, Excel, other languages. There's a type provider that allows you to connect into R. So if you're doing any type of statistical analysis, you can go in and use the power of F# in conjunction with the power of R. It's really, really sweet. XML documents, and the one I love to demo, and the reason I like to demo it is because it doesn't require an internet connection and it doesn't require a database, is for regular expressions. How many people like writing regular expressions? Exactly. So I actually don't mind it, but the way that I make myself not mind it is I like to make sure that all my captures have nice names on them. Now, let's jump over to VS Code again. and scroll through those examples. And all right, here we go, other window. So this one I just brought in. We have a package manager in F# that's called Packet. It's pretty nice, manages your dependencies a little bit better than NuGet, but still plugs into NuGet, so it's pretty nice. But I brought in this package called f#.text.regex provider. This is something that if you do use the book, I have this example in there, but the code has moved from one library to another to another. The book hasn't been updated to reflect that, but it's really a pretty powerful type provider. It was my understanding is it was originally developed kind of as a proof of concept to see if it could actually work, and to show kind of the flexibility of how beneficial type providers can be to your code. I like it because I do like regular expressions for the most part. But you can see I've got this regular expression here, color regex. Now, that doesn't look like how we normally define a regex, does it? Usually it's like new regex. This is a type. Like, okay, that's a little weird. I've got a type that's based on a regular expression, and I like that it's got a generic syntax. One thing to be very aware of here, notice that space on line 232. I just highlighted it. I'm sorry, it's probably hard to see in the back, but this space here, because of the generic-like syntax, is very, very important, because if we get rid of that, notice it's highlighted. This is just one of the quirks of the language. It's trying to treat this string literal as a quotation expression. So getting rid of that white, or making that white space in there, will trick the compiler into doing what you actually want it to do instead of making it do what it thinks you're trying to do. But we've defined a type for our regular expression. And what this is doing is behind the scenes, it's parsing that expression. So it knows some things about the structure of it, and it's going to do some interesting things behind the scenes. Now, you work with named captures. Typically, you've got to pull them out of the groups collection, right? It's a dictionary of names. Well, that kind of sucks, right? Like, you fat finger something. Who's to say, I've named it red here, and I say R in the hard-coded string to pull out the value. What if I decide, okay, you know what, I can't read this. I can't read this thing anymore. Or what just happened, and you insert some text, and who's to say that this change that I just made, changing red to R, is actually going to get propagated through all of those strings? What the type provider is going to do, and if you're watching the bottom of the screen, you probably already saw this, but I'm going to send some code down. We have F# Interactive, and I'm going to bring in a few namespaces and a library. I'm going to define that, so I'm just executing it. You can see it running at the bottom. I'm going to create a function that's either going to return some or none. And I've got to bring in system. That's what I get for doing this one at the last minute. There we go. So now if I go here and run this last line of code, of course, mono's breaking. Crap. What did I break? Oh, because I didn't bring it. Okay, yep, I didn't get this one quite working. I was going to convert it over to the system.drawing, and I didn't bring that in. I've got a bad image format, so it's trying to do like the 32-bit instead of the 64. But we can still look at the code. So let me get rid of this. And we'll still see the overall behavior we expect. So we've got this type. Red, green, and blue are our captures. And we can say in here, if m.success, have we matched? We're going to take our color. We're going to pass it over to a new instance of that color regex type. And we're going to invoke the typed match method on that color regex type. So this regex type provider has generated this type for us behind the scenes, and it largely resembles the built-in regular expression classes, but instead of having to have things like m.captures, or m.groups, I'm sorry, notice we have property names here instead. It's match.red, match.green, match.blue. And if I come back up here and I change that from red to R, I have red squiggly. The compiler has found that regular expression has changed, and it will stop me from compiling and deploying code that is known to not work because the regular expression no longer matches what the code was expecting it to do. That's powerful. And that's why we rely on a type system. Because now, if I didn't have a unit test there, I've caught it immediately without having to do any extra work because the type provider has already done that. Now, type providers do come in two flavors. There's generative and erased. So just like the units of measure can be erased, the types that the type providers can generate can also be erased, and basically everything just gets treated as object behind the scenes. And then there's some that will actually generate types that remain and are part of the compiled assembly. I do have, if you really want to see how this mechanism works, because it's really cool, I mean, it's running as part of the compiler itself. I've got a Pluralsight course on building type providers. The course is specific to erased providers, but I also have a blog post linked from there that talks about how to do a generative provider. So it's very cool stuff. There's lots of there's lots of different type providers out there, but I hope you've gotten something out of this. This was I love F#. I think there's lots of things. Again, as Brian has said in a previous talk, that this is one of those things that Microsoft really has going for it, and they don't seem to be aware of just how powerful of a tool they've created. So thank you very much for your time, and enjoy NDC. And Brian, who gets the books?